So this is technically the last part of this module. So you guys, we're in the home stretch now. Woohoo. But okay, so what we're going to be figuring out is pH of a weak acid or base using Ka or Kb. And like I said, a strong acid dissociates completely and a weak acid doesn't. So you have your dissociation constants, which is your Ka or Kb. So since we don't know how much your acid is dissociating at that given time of whatever we're going to solve for, that's why we use our ice tables and Ka and Kb to solve for it. Oop, yeah, we're good. To solve basically for your concentrations of H plus and OH at that given time, given how much it's dissociating by our Ka or Kb. Which I know it's kind of weird to hear me explaining it, so I'm just going to walk you through a problem. So let's say that we're trying to find the pH of a 1.5 molar hydrofluoric acid, and then the Ka of hydrofluoric acid is 7.1 times 10 to the negative 4, which, okay, I feel like I should have said this in the last video, but we weren't really using them yet. Your Kas and Kbs on exams and stuff, they're going to be given to you guys on like a chart or within the problem itself. It'll tell you this acid has a Ka of so-and-so, or this base has a Kb of so-and-so. And if not, there'll be a separate chart which you can flip to find the Ka and Kb corresponding to what you're looking for. So you don't have to memorize them, like, don't panic. So, okay, we're going to set up our equation, which is hydrofluoric acid aqueous plus water liquid. And then in this case, we do have the double arrows because it's a weak acid, so it can go back and forth. And we're going to have our hydronium ion aqueous plus our fluorine ion, also aqueous. So ice table, I is for initial, and we have 1.5 molar. Condensed states don't matter in equilibrium, they just become 1, so we don't have to fill that out. And 0 for our products because we haven't started them yet. And then our change, like I said, this isn't a strong acid, so we don't know how much it's changing by. So we just supplement it with X. Again, water doesn't matter. So then this is plus X, and this is plus X. And at equilibrium, we're going to have 1.5 minus X, and this is just going to be X, and this is going to be X. So we can write our Ka expression as H3O plus F minus all over HF. So then that becomes X squared because it's your X times X. So it's like we're replacing them for them at 1.5 minus X. Oof, I don't have enough room here. So I'm just we're gonna move this over here. So then it's 7.1 times 10 to the negative 4 gives us our X squared over 1.5 minus X. Right. So to do this, you would multiply this over and so forth, but this X is going to cause us to basically do the quadratic formula. But there is a way in which we can disregard this X, and that is if the difference between our initial concentration and our Ka is over 1,000 times, like larger. So if I were to do 1.5 divided by 7.1 times 10 to the negative 4, as long as the number we get is larger than 1,000, we can disregard the X. And let me do that real quick because I forgot to write down the value, but I do know it's larger than X. larger than 1,000. Yeah. So we get that this being divided is 2,126.67, which that is larger than 1,000. So then we can just disregard this x. Like if it was never there, it can't hurt us. We won't do the quadratic formula. So then now we just algebraically do this. 7.1 times 10 to the negative 4 times 1.5 is equal to x squared. So then this is 1.065 times 10 to the negative 3 is equal to x squared. We take the square root and we get 3.26 times 10 to the negative 2 is equal to x. So then now that we have our value of x here, that can be plugged in over here for this x, which is our hydronium ion. So we can find our pH by doing the negative log of our x, which is our hydronium ion in this case, 3.2 times 10 to the negative 2 to get a pH of 1.49 or 1.5, depending on how you guys round and so forth. But yeah, so like I said, when it comes to disregarding the x, so if it's, I'm gonna make a note over here for you guys. Okay, yeah, that is thin. I didn't remember. So disregard x on denominator. If initial concentration divided by Ka or B is greater than 1,000, or if the exponent on your Ka or Kb is smaller than negative 5. Which, okay, if you guys remember, negative 5, smaller than it would mean like negative 6, negative 7, negative 8. Just because if it's a negative number, kind of like the bigger the number, the smaller it actually is because it's further away from 0. Just because I know it gets kind of funky with the negatives. So yeah, so your x can be disregarded if initial concentration divided by your Ka or Kb is greater than 1,000, or if the exponent on your Ka and Kb is negative 5 or smaller. So in this case, we had a negative 4, which isn't negative 5, so we had to check if it was greater than 1,000 to see if we could disregard the x. Which thankfully we could, because then we would have to do the quadratic formula, but you guys don't have to worry about that, because I doubt they would give you a problem with the quadratic formula, because that's unfair. So yeah. So that's how you find your pH using a Ka. So let's do one now using a Kb. Which, yeah, like I've said before, if I'm erasing this too quickly, you guys can just pause the video so that I don't erase what you guys need. I'm going to leave that up there. But, okay, let's take, for instance, 2.4 molar of methylamine, and our Kb is 4.4 times 10 to the negative 4, which, if you guys don't know what methylamine is, it really is just what it's saying. Your methyl, which is a CH3, and then your amine, which is an NH2. It's bringing back OChem for you guys, in case you don't remember. But yeah. So then plus our water yields CH3 NH3 plus aqueous, and an OH minus. So, okay, with this one, if you didn't know if this was donating the H or if, so with this problem, if you didn't know if your methylamine was donating an H or accepting one, like if it was the acid or the base, it's kind of given to you in the problem because it gives you a KB, and a B is for your bases. So then you would know that your methylamine is a base. So that's why you would add the water. You would add the hydrogen to this one and take it away from this one so that you end up with your OH that tells you that you're dealing with a base anyway. Right. So then we do our ice table. So initially we have 2.4 molar. This doesn't matter. 0 and 0. Our change, we don't know it. It's X, X, and X. And then here we have 2.4 minus X, and this is just X. So then KB expression is CH3 NH3 plus times OH minus over our methylamine. I forgot the 3. There we go. Which is equal to X times X over 2.4 minus X. Okay, so I'm going to move the problem over here because my hubris, I keep doing this. So then we're going to have 4.4 times 10 to the negative 4 is equal to X squared, just because X times X is X squared, over 2.4 minus X. So since this is a negative 4, it's not smaller than negative 5. So we're going to have to check that our initial, which is 2.4, divided by our Ka, or I mean Kb in this case, which is 4.4 times 10 to the negative 4, is greater than 1,000, and in this case it is. It gives you about 5,454 or something around that. It's bigger than 1,000. So then we can disregard this X and solve algebraically. Times 2.4 is equal to X squared, which gives me 1.056 times 10 to the negative 3. Oh my god. Negative 3 is equal to X squared. We take our square root so that we can solve for our X, which is 3.25 times 10 to the negative 2 is equal to X. So then in this case, we're going to be solving for POH first, because that's what our X would be substituting in here for OH, right? So OH to OH. So we do the negative log of 3.25 times 10 to the negative 2, and that gives us 1.48. So then to find pH, we just do 14 minus 1.48, which would give us 12.52. Yes. And that's our pH of our methylamine, which makes sense because our number is greater than 7, and this is a base. So that's also a way to double check your guys' work, is like I said, if pH is less than 7, then it should be an acid. If it is 7, it's neutral, and if it's greater than 7, then it's a base. So if we had gotten a number less than 7 in this case, we would have to double check our work because this is a base. It should be greater than 7. So yeah, that's all there is to Module 10.